Thank you for the kind introduction. It's a great pleasure to be here today. What I'm going to hope to accomplish today is to give you some insight into the work going on in our lab in the area of so-called mixed-dimensional van der Waals heterostructures, specifically focusing on electronic and energy applications. Before we get into the details of the talk, I'd like to make some introductory comments about nanomaterials in general. These comments are based upon the following report, which is shown here. This is a report that was commissioned by the National Science Foundation. Mike Rocco from the National Science Foundation asked Chad Merkin and myself to go around the world and ask the following two questions. What was accomplished in the first decade of the nanotechnology initiative, and where was the field going to go over the next decade? And it led to this report where we outlined where the field was going by the year 2020. We're now in the year 2018. This report was written in 2011, as you can see, so you can see how well we did if you check out this report. There's no way I'm going to summarize the 600-page report tonight or this afternoon. Instead, what I'm going to do is give you three major bullet points, which I hope you can remember throughout the talk today, to identify what's different about nanomaterials compared to bulk materials. The first is when you go to very short length scales, the nanometer length scale, the properties of matter become dependent upon size and shape. This is very different than macroscopic length scales. If I think of an ice cube or a glacier, they both melt at the same temperature, even though they're very different in size. At the nanometer scale, if I have a 3 nanometer diameter particle or a 1 nanometer diameter particle, the melting temperatures could be hundreds of degrees different, and that's true for all properties. This is the great benefit of nanoscience. We have a new knob to turn to realize new properties, but it also leads to a severe challenge in that any inhomogeneity or polydispersity in structure leads to inhomogeneity in properties, and this has confounded many efforts to take nanoscience to nanotechnology. Second major difference is at the nanometer scale, the surface to volume ratio becomes very high. In the limit of an atomically thin material, every atom is on the surface, and therefore surface chemistry and passivation plays a key role in determining the properties of matter. And then finally, at the nanometer scale, the length scale over which electromagnetic fields are screened are bigger than the materials themselves, and this leads to a variety of exotic effects such as excitons, the ability to tune properties with externally applied fields. Each of these concepts will be showing up throughout the talk today. And while you could apply those principles to any class of nanomaterials, today I'm going to be focusing specifically on low-dimensional nano-electronic materials. The first one I want to introduce is graphene. This is a two-dimensional form of carbon, one atom thick sheet of carbon and a honeycomb lattice. Graphene itself is of high interest. It has very high charge carrier mobility, which means electrons move through it quickly and can be used for high-frequency electronics. It's also conceptually helpful for imagining other low-dimensional forms of carbon, in that if we were to cut out this green shape here and roll it up into a sphere, we'd get a zero-dimensional form of carbon known as a fullerene, whereas if we were to take a rectangle, cut that out and roll it up into a cylinder, we'd get a one-dimensional form of carbon known as a carbon nanotube. And I'd like to stress that conceptually the width of this rectangle could have been varied, which would vary the diameter, or the angle at which this is cut out with respect to the graphene lattice could also be varied. And so there's not just one carbon nanotube, there's 300 distinct carbon nanotubes based upon the diameter and the twists with respect to the graphene lattice, each with a different set of properties. Or we can imagine taking graphene and stacking it up into 3 dimensions, where the bonding between the layers is van der Waals bonding, and this is graphite. Of course, historically, graphite came way before graphene. It was the exfoliation or peeling away of graphene layers from graphite that won the Nobel Prize in Physics in the year 2010. And the reason that I point that out is that there are many other materials that are layered and can be exfoliated down to the atomically thin limit, including boron nitride, which is electrically insulating, molybdenum disulfide, which is a semiconductor, relatively wide band gap, and typically doped N-type, which means negative charge carriers. Phosphorine, which is the phosphorus analog of graphene, also semiconducting. And boraphene, which is based upon boron, that's metallic. And the point of this slide is to note that these materials encompass all electronic properties from highly insulating to highly conductive. And as a result, if we had a means of stacking them together into heterostructures, we should be able to make any and all electronic devices out of this class of materials. And that brings me to the concept of a van der Waals heterostructure. Since the bonding between these materials is a weak van der Waals interaction, we can just stack them together and form heterostructures without worrying about the lattices being perfectly matched. And this is in contrast to previous materials that have been explored for heterostructures. The concept which we're pushing in our lab is to take this notion, which historically has been applied to two-dimensional materials, and to expand the concept beyond 2D. So we can imagine taking a two-dimensional material like graphene and decorating it with zero-dimensional molecules or quantum dots, or taking two-dimensional materials and decorating them with one-dimensional carbon nanotubes, or taking a two-dimensional material, mounting it on a bulk material. And these van der Waals heterostructures would be mixed-dimensional because they're made up of more than one dimension. And that has two advantages. One is it broadens the palette of possible materials to choose from, giving a more diverse set of possible heterostructures. But more fundamentally, as you change the dimensionality of a system, quantum confinement effects change qualitatively. And therefore, we now have discontinuous changes in the nature of the material across the hetero interface. This leads to new physics, new properties, and ultimately new applications. So this is what we want to build up to today, how we can make these things and how we can use them in real-world settings. Towards that end, what I'd like to do today is go through this outline. Begin first with how we realize the constituent nanomaterials that go into the heterostructures. How we then use methods known as additive manufacturing, such as solution processing or printing, to build them up into heterostructures, and then ultimately conclude with the types of devices and applications enabled by these class of materials. So first, let's talk about the constituent materials themselves. Now, as I alluded to in the second slide of this talk, when you go to the nanometer scale, properties depend upon size and shape. And the problem is that when you try to synthesize a population of nanomaterials, you rarely have perfect control over size and shape, and therefore irreproducibility from device to device. This problem is perhaps most famous for the carbon nanotube. As I mentioned, there's 300 distinct carbon nanotubes, and when you grow a sample, you get a mixture of all of them. And so the question is, how with atomic precision can we separate one carbon nanotube from another in a manner which is scalable and therefore can be implemented in a manufacturing environment? Our basic idea was to recognize that the size of these nanotubes is very similar to the size of biological macromolecules like DNA. And as a result, we should be able to go to biochemistry, which has developed exquisite methods for separating DNA from RNA from polysaccharides, and apply that to nanomaterials. In particular, the method called density gradient ultracentrifugation is widely applied in biochemistry. And how it works is you load a centrifuge tube with an aqueous or water-based solution, and you introduce an additive as a function of depth. And that additive allows you to tune the buoyant density of the medium itself. So you have a gradient in the density of the solution. If we then load into that centrifuge tube a distribution of nanomaterials and turn on the centrifuge to drive sedimentation through the gradient, those materials will sediment until their density matches that of the gradient, at which point they'll simply float. And therefore, we're just using buoyancy forces to separate the nanomaterials by their density. Density depends upon size and shape, and therefore we achieve size and shape separation. This is a photograph of one of our centrifuge tubes. Initially, a carbon nanotube solution looks black because it's absorbing in all wavelengths due to the range of diameters that we have. However, after running it through this process, we see visibly colored bands. This is a pink band we can see with our naked eye. Evidence that we separated by diameter with atomic precision, and therefore by optical properties. This is a pretty good day in the nanomaterials lab when you can see with your naked eye that you've achieved an atomic level of control. The beauty of this method is that it's completely general. While we first did it with carbon nanotubes, essentially all nanomaterials can be separated in this manner. The next target we had was graphene. As I mentioned before, graphene is derived from graphite. So what we do is we take graphite powders. Graphite is just pencil lead. We grind it up, we put it into water. We disperse it with an appropriate surfactant, which is basically a soap molecule. So we have soap, graphite, and water. We put it into a beaker, which gives us this black dispersion you see here. When we run it through the density gradient process, we see banding in this case, and the bands are now separated by the thickness of the graphene. So we get single layer, bilayer, trilayer graphene. So again, the raw materials are soap, water, and pencil lead, and what we get out is a high-performance electronic material. This is something that significantly adds value to the underlying raw materials. We then thought we could easily apply this to all the other two-dimensional materials that I mentioned. The next target we had were the so-called transition metal dichalcogenides, such as molybdenum disulfide. The problem is that molybdenum is much lower in the periodic table than carbon, which means that its density is much greater. And that's a problem because the maximum density in our gradient is fixed. And if you just use a traditional soap to disperse molybdenum, you find that its density exceeds that of the limit of our gradient, even in the atomically thin limit, and as a result, everything crashes out when you try to separate it. So the question then becomes, how do you take something that's intrinsically dense and artificially lower its buoyant density in aqueous solution? The way you do this is you use now a soap or a surfactant which has got a much longer tail to it than the small molecules I showed you before. And this tail will then hydrate. In other words, it will have tightly affiliated water molecules with it. Since water is much less dense than molybdenum disulfide, the aggregate gets reduced in density and therefore falls into the range of our density gradient medium. And so just by changing the surfactant chemistry, we now get beautiful separation. The same banding I showed you before is now achieved not only with carbon, but also with molybdenum or tungsten disulfide. Once we realize the benefits of having a larger hydration layer, we then return to the top of the periodic table, looking at, in this case, boron nitride, right next to carbon. The density of boron nitride is essentially the same as graphene, but when you use these thicker hydration layers, you now see much more exquisite separation. If you remember back to the graphene slide, the bands were kind of diffuse and overlapping. Now we can see that there are very tight bands, and you can count them. 1, 2, 3, 4, 5, 6, 7, 8. We're separating boron nitride with atomic precision, single layer, bilayer, trilayer, etc., as we confirm subsequently with cross-sectional atomically resolved transmission electron microscopy. At this point, the bands are so well separated that you can go in with a pipette and extract them and have very high monodispersity. So at that point, you think maybe we've solved it, we can separate anything, but there is a problem, and that is that this is all done in aqueous solution, water-based solution, since it was born out of biochemistry. And there are some materials, such as black phosphorus, which is the graphite, or the phosphorus version of graphite, which we would like to exfoliate down to phosphorine, where this material is unstable in normal ambient conditions, and therefore you would expect it may react if you put it into water. And in our first trials of trying to separate this, we had a problem. It quickly oxidized in the water environment. It turns out, though, that the actual mechanism for black phosphorus degradation is not water alone, but the combination of water and oxygen that's present in air. And as a result, if you deoxygenate your water by sparging it with an inert gas like argon, then you can put black phosphorus in, it does not react, and then you can use density gradient processing to separate out the phosphorine sheets. I have to admit, when we did this, there was some skepticism in the community that probably the phosphorus was being damaged through this process. And so we proceeded then to take the resulting atomically thin flakes, disperse them onto a substrate, and then wire them up to the outside world with electrodes, and then measure the resulting electrical properties. This is in a so-called field effect transistor geometry, and there's two important metrics in the transistor. One is the switching ratio, the on-off ratio, which you want to be high, and the current through the device, which you also want to be high. So you want to be up here for a well-performing transistor. And what we can see is that with these aqueous or solution process black phosphorus, that the performance is just as good, if not better, than all of the literature precedent, which had been achieved with less scalable manufacturing methods. So the properties are, in fact, preserved. In addition to electronic properties, this material of black phosphorus is quite interesting in that it's optically active in the near infrared, and the near infrared is the wavelengths of telecommunications. And what we've shown very recently is we can take the solution process black phosphorus, disperse it onto substrates which are fabricated to have silicon photonic cavities, and see very strong light emission right at 1.55 microns, which is the center of the transmission band for telecommunications. So again, we're taking a material, processing it in water, and resulting from that a high-performance optoelectronic material. The only problem, though, is that in this process, as you saw, we're using soap molecules to disperse them, and those soap molecules are not electronically active. They will occlude charge transport into the active material. Particularly if I were to make a percolating film out of those flakes, the soap molecules would occlude access for charge transport through the layer. And so what we've done very recently in our lab is figure out a way to get away from the use of the surfactants altogether. The way we do this is to change the solvent in which we're doing the dispersions. In this case, using a mixture of solvents, an ethanol water mixture. This particular two-dimensional material called indium selenide, we can see if we're in water alone or ethanol alone does not disperse well, we would need surfactants to disperse it in those limits. But for intermediate co-solvent mixtures, we can satisfy the surface energy needs of indium selenide and get nice dispersions now without any surfactants being present. The advantage here is that we can now take the resulting flakes, we can wire them up to the outside world, measure their properties, and we find that the transistor metrics, the photo response are all superlative, so this method also preserves the underlying electronic properties. But what's more interesting and relevant for today's discussion is that if we now take these flakes, cast them onto a surface into a percolating film, due to the absence of any surfactants that are present, we get effective charge transport, and therefore this is highly amenable to additive manufacturing methods like printing, where we now have percolating networks of these sheets. And we find that the current flow through these ethanol water dispersed samples is substantially higher than when we use surfactants due to the elimination of those barriers to charge transport. What this then allows us to do is to make a series of dispersions out of all the materials that I mentioned: black phosphorus, molybdisulfide, tungsten disulfide, tungsten diselenide, indium selenide, etc. You can see that these inks, if you want to call them that, have clearly distinct optical properties since they're all different semiconductors. And importantly, when we make devices out of them, the current flow through them is effective, and so we can now make percolating networks. All we need to come up with is some way of depositing them where we want on a substrate with respect to some contacts to make electronic circuits. An important part of this is that the underlying methodology, the density gradient methodology, is one that was developed in biochemistry, as I mentioned, and as a result has already been scaled up by the pharmaceutical industry, and as a result it was straightforward for us to scale up our process. We formed a company called NanoIntegris that took the density gradient process, scaled it up by 10,000-fold, and is now selling these highly homogeneous nanomaterials globally to about 1,000 customers in 40 countries. In fact, my student, Nathan Yoder, who scaled this process up, did so well that we still have inventory that we haven't sold yet. He produced more than the worldwide demand for these materials. So it's really a business development problem more than a technical problem at this point. Okay, so hopefully I've convinced you that in our lab we have methods for forming highly homogeneous or monodispersed nanomaterials in scalable quantities to meet market needs. But what we have now is a dispersion. This is a water-based dispersion with some materials in it. What we now like to do is use those as an input into some additive manufacturing process to put them where we want on the substrate. In other words, we want to convert from a dispersion to a printable ink, something that we would print to an inkjet printer, for example. At first glance, it sounds like it would be easy. I already have it in solution. Maybe I just put that in the ink cartridge and I go to town. The problem, though, is that the rheology, such as the viscosity of the ink, is very important in getting effective printing. In fact, if I take a ballpoint pen and I look at the ink in a ballpoint pen, there's 40 different components in that ink to make sure that it only comes out when I'm writing, it doesn't bleed all over the paper, it dries quickly, and works on a variety of different surfaces. We'd like to have all of those properties now in a nano-electronic ink, and to do it in a manner where we preserve the electronic properties while having the right printing, drying properties as well. So this is a multivariable problem which is going to require a strategic choice of additional additives to the dispersion. If you look at inkjet printable inks, they're often derived from alcohols like ethanol. The problem is that nanomaterials like graphene disperse very poorly in ethanol, so you do need to add something to get them to go into ethanol. What we end up using is a polymer called ethyl cellulose. Ethyl cellulose is derived from plants. It's a cellulosic polymer, so it's environmentally friendly, as is the ethanol that we're using for the solvent. And what ethyl cellulose allows you to do is to pack into the ink 100-fold higher levels of graphene than you have without the ethyl cellulose. And when you get to these high loadings, now the viscosity of the ink is highly tunable, and you can dial it in to match that of your favorite printing method. For example, if I dial in the viscosity to match that of your inkjet printer in your office, I can then add these inkjet printable graphene inks and literally print it just like you do on paper in your office, beautiful lines, now not of a black ink, but a graphene ink that's electrically conductive. We see that the lines have very high fidelity, there's no drying effects or other corruption to the printed structure. There is an issue though. When I first printed, I still have the ethyl cellulose in there. That's electrically insulating, and therefore the film will not be conductive. So I need to somehow get that out. And the way we did it initially was to just heat it up to a high temperature, 250 degrees for 30 minutes, and literally burn out the ethyl cellulose. Most of it's removed via gas phase byproducts. There's a small amount of amorphous carbon char that remains. And that char is templated by the graphene to have high so-called sp2 content, which means it's electrically conductive. So the ethyl cellulose eventually becomes a conductive glue that stitches together the graphene flakes in the printed structure. It also helps reinforce the film mechanically, and therefore we can print this on flexible substrates like plastics and flex them and maintain electrical conductivity for flexible electronics or wearable electronics. So this all looks good. The only thing which may catch your eye as being problematic is this temperature. 250 degrees C is pretty hot. If I wanted to print this on paper, the paper would be long gone way before I got to 250 degrees C. So how do we overcome that problem? So the trick is to not use a traditional oven or furnace, but instead use light as the source of energy. We use a pulsed xenon lamp, which is a high-intensity broadband light source. Graphene is black, and therefore it absorbs all wavelengths. And consequently, that light is absorbed in the graphene, not in the underlying substrate. So only the graphene is hot, and therefore you can use a low-temperature substrate like plastic or paper. The other advantage of this process is that this is a pulse lamp, which means in 1 millisecond, 1,000th of a second, we get the same curing that we get with 30 minutes in an oven. And as a result, the curing time is now faster than the printing time. So if you imagine a roll-to-roll manufacturing process, you don't need to slow down the roll to cure the ink. It's happening just as fast, if not faster, than the printing itself. And so we'll see. I didn't check the movie. We'll see if the movie works today. It does, great. So you've now actually seen this printing in action. This is an extrusion-based printing nozzle where we're forcing the graphene ink through the nozzle as we move the substrate underneath. In this case, we're printing an electrically conductive interdigitated array of electrodes, which can be used in an electrochemical biosensor and other applications You can see this is very high fidelity, a rapid printing methodology, much faster than going into a clean room and patterning this via some sort of photo or e-beam lithography. Very good for rapid prototyping. The other thing I wanted you to take away from this video is that we're extruding the graphene through the nozzle. If we had changed the viscosity of the ink such that immediately upon extrusion it solidified, then we could not only make a two-dimensional pattern, but also build up into the third dimension for so-called 3D printing. And that's something that we've achieved. We've increased the solid loading in the ink to be something in the order of 50%. So we have just as much solid as solvent in these inks. It's now more of a paste-like ink. And when you extrude it through the nozzle, it immediately solidifies and allows you to build up into the third dimension. So now we can make structures that are millimeter or larger on nice scale in all three dimensions. In this case, we made graphene cylinders via 3D printing. And because the loading is so high, in this case, we're already percolating through the film. We don't even need to cure it. It's electrically conductive, and in this case, we're passing current through to drive this blue light-emitting diode. Also, the mechanical properties of graphene are preserved. It's mechanically flexible. So we now have a tailorable three-dimensional structure that's electrically conducting, mechanically flexible, chemically inert, and it turns out is also biocompatible, which suggests opportunities to use it for biomedical applications. In particular, in collaboration with our medical school, we began exploring this 3D printable graphene as a conductive bioscaffold. This is used in patients that have nerve damage. And how this is done historically is the surgeon would go in and measure the extent of nerve damage in the patient. Once they know the size of the nerve damage, they close the patient up, send out the dimensions to an external fabrication facility to make a tubular nerve conduit, bring the patient back in for a second surgery, and then install the implant. In contrast with a 3D printer, the surgeon can now open up the patient, measure the size, have it printed in the operating room in the time scale of minutes, perfectly customized for that patient, and then implanted in the same surgery. This is clearly more efficient, reduces the amount of time under anesthesia, reduces the probability of complications during surgery, and we think it's really going to be game-changing for how implanted surgeries are done. The bottom line is that the strategic choice of the right additive to your ink allows you to dial in the viscosity for a range of printing methods, including, as I said, inkjet printing and 3D printing. It also works for gravure and screen printing. Screen printing, as you may know, is used in printing t-shirts. You can make wearable electronic devices straightforwardly using this type of methodology. All of these inks have also been commercialized via a company called Sigma. More recently, we've been going beyond graphene, some of the other materials that I mentioned, such as molybdenum disulfide. This material can also be dispersed using ethyl cellulose. We can dial in the viscosity by changing the volume fraction. We get very nice printing of now molydisulfide on glass substrates or plastic substrates, and then subsequently we can remove the ethyl cellulose via thermal or photonic annealing. Because this is a semiconductor, the applications we're pursuing are photodetectors. These are devices that convert light into electricity. What's interesting is that depending upon how we anneal the sample, we see very different performance. If we use thermal annealing, or TA, we find that we get photodetectors that are very fast in their time response. The responsivity is better than literature precedent, but not as good as we get with photonic annealing, or PA. For photonic annealing, we see higher responsivity, but at a reduced time response. And the reason this is true is that when we do the photonic annealing, as I mentioned, it occurs in 1 millisecond, and all the gas phase products are liberated very quickly, which leads to a very open or porous structure. Porosity is good for photoresponsivity, but bad for time response. Whereas thermal annealing is a more controlled process, we get better stacking of the flakes, giving you better time response, but compromised responsivity. So the ink not only matters, and the materials not only matter, but also the way in which you cure it will influence the resulting properties. The other case that we have been exploring is hexagonal boron nitride. This material, as I mentioned before, is electrically insulating. In this case, again, we can tailor the viscosity by orders of magnitude by the solid loading. And in particular, if you operate in this direct ink writable range where it's very viscous, you get relatively thick films. And when you burn out the ethyl cellulose, what you get is a porous film. So what we have now is a film that's porous but electrically insulating. It could be used for membrane applications like water filtration. Or the other place where this could be quite useful is in a separator in a lithium-ion battery, where you need to have ions transmit through the separator, but you need to keep the two electrodes from shorting out with one another. And so we've begun exploring this. We're now taking our boron nitride, we're casting it into films, using it as a lithium-ion battery separator. The traditional materials used for this application are polymers, and that's a problem because if the lithium-ion battery gets too hot, the polymer becomes compromised, and that leads to shorting of the battery and catastrophic failure. I think we've seen in the news some catastrophic failures of lithium-ion batteries, which can be partially attributed to the separators that are being used. In contrast, boron nitride is a ceramic material, very thermally stable. We can heat this up to 900 degrees C without any change in properties, whereas the traditional polymer-based separators break down at about 250 or 300 degrees. This gives you significantly enhanced thermal stability and enhanced safety as a result in lithium-ion batteries. The other limit for boron nitride, though, is to utilize a biocompatible polymer and to keep it in the resulting printed structure. That has two advantages. One is that because the polymer is present in the printed structure, you maintain the properties of the polymer, which are mechanically flexible. We can roll these boron nitride sheets up into cylinders, which is very strange. Boron nitride is a very brittle material normally. We've also shown that it's biocompatible. In particular, we've been using these as cell scaffolds for driving stem cell differentiation, which is quite useful for a variety of tissue engineering or regeneration applications. So again, I think some of the nearest term highest value targets will be in the biomedical arena. With that said, let me move on to the final topic, and that is we're going to try to put everything together that we've talked about today, and taking these diverse range of materials and now stacking them together into heterostructures in a manner where the combination is better than the constituent parts. So the first example I want to give is a mixed dimensional heterostructure, taking a one-dimensional single-walled carbon nanotube and combining that with a two-dimensional molybdenum disulfide. Molybdenum disulfide is a material that has an N-type behavior or negative charge carriers dominating. Nanotubes are P-type or positive charge carriers dominating. And when you integrate them together into a heterojunction, what you should get is a so-called p-n junction diode. The p-n junction diode is not a new device. It was invented in the 1930s, and it's the basis of all modern-day electronics. The key characteristic of a diode is that its current voltage curve is asymmetric or rectifying. By that I mean at positive voltage you see a lot of current, and negative voltage you see very little current. And this device, in the light blue curve, shows a nice rectifying curve. Again, this is not new. The diode's been around for 80 years or so. But what's different about this diode is because the constituent materials are atomically thin, if you apply a vertical electric field to them, that electric field will not be screened. At least the screen length is longer than the size of the material, and as a result, that field will have dramatic influence on the charge carriers, and as a result, the resulting current voltage curve. So what we see here is, as we change the voltage on that third gate terminal, that we dramatically change the current voltage curve, influencing the rectification ratio by 5 orders of magnitude. So what we have now is a gate-tunable diode. This is a new circuit element. Among other things, it shows a so-called anti-ambipolar transfer curve, one which is potentially useful for high-frequency electronics such as Wi-Fi technology. This device, since it's a diode, also has a strong photo response, but because it's made up of two different types of materials, it responds to light at two different wavelength ranges. The moly disulfide makes it active at visible wavelengths, whereas the carbon nanotubes make it active at near-infrared wavelengths. So you get a two-color photodiode. due to the fact that we have two different materials present in the device. Also, as we tune the gate voltage, we can turn on and off either portion of the spectrum, so we can convert it into a single color diode with a tunable wavelength based upon the voltage that's applied. So that's pretty interesting, useful for a photodetector. But where most people get excited about PN junctions is not for a photodetector, but rather as a solar cell. And the problem is that for these two materials, while they do show a photo response, they don't show a photovoltaic response. In other words, they do not work as solar cells. And as a result, we had to develop a next generation design. We got rid of the nanotubes and now utilize a zero-dimensional organic semiconductor called pentasene. When we combine pentasene with molybdenum, we still get the same anti-ambipolar current voltage response I showed you before. But due to this combination of material and their band alignment, we now anticipate a strong photovoltaic response. And this is in fact the case. If we look at these resulting photovoltaic or solar cells, in the dark, which is the black curve, and the red, which is the curve in the light, we see dramatic changes in the current flow. And importantly, what we see is a finite current flowing at zero applied voltage. We've successfully converted the light into electricity, and as a result, we have a functioning solar cell. We've also looked at this in more detail using advanced spectroscopic methods, which allow us to understand the dynamics of the resulting charge carrier motion. The point I want you to take away from this slide is that by utilizing this zero-dimensional, two-dimensional, mixed-dimensional heterostructure, we get tenfold longer timescales for charge separation compared to using 2D materials alone. A longer timescale for the charge separated state gives us more time to get the charge out of the device and leads to improved photovoltaic efficiency. So this all looks good, very promising for solar cells. The only issue, though, is that in the devices such as this device here, you can see that the electrical contacts are off to the side and far away from the junction region. The junction region is where all of the action is. And getting the current out through these long distances leads to ohmic losses and therefore reduction in efficiency. So what we need is some means of taking this device and making it much more compact to more efficiently get the charge out. And this is challenging because if I have atomically thin materials and I just put electrodes on the top and bottom of them, if there's any defect in that material, they'll short out the device. And so that's basically a losing proposition to just directly stack them. So we have to get the contacts close, but not directly on top. And this really confounded us and many in the field for many years until just a few months ago, my student Megan Beck came up with a very clever solution to the problem. So I'll try to step you through it. What she did is she said, let's take the first material, like molybdenum disulfide, and put it on the bottom and connect it with some contact, this gold contact here. Then I'm going to put on top of it an insulator, which is in this case aluminum oxide, and it's going to barely extend over on top of the molybdenum disulfide. She then puts on the next material, in this case it's black phosphorus, but it could be whatever you want, and then put a top contact here. So you can see the two contacts are on top of one another, but this insulating alumina layer makes sure that they never short out. So there's no chance of shorting in this device. The current pathway then is from this electrode into the molybdenum disulfide and then around the corner and back up into the top contact. So this semi-vertical geometry ensures no shorting and very short distances to the contacts, which gives you significant enhancement in photovoltaic efficiency. It also has other advantages. You have space here to put in additional electrodes at the top gate or bottom gate, which gives you further tunability over the device. This type of concept is completely enabled by van der Waals materials, because you don't need lattice matching. You can just layer them wherever you want and whatever geometry you want, especially going up into the third dimension. The net effect is improved device performance. Not only do you see the photovoltaic effect improved, but you get further tunability over the response. And this type of Gaussian current voltage curve is something that's now being explored for next generation computer architectures. The next example I want to give is another mixed dimensional heterostructure, but in this case it's not different materials, but made out of one material alone. Specifically, we're going to look at molybdenum disulfide again. It's a two-dimensional material. But if you have a polycrystalline molybdenum disulfide material, then you're going to have intersections between the crystalline domains called grain boundaries, which are going to be one-dimensional in nature. So the interplay between the one-dimensional grain boundaries and the two-dimensional molybdenum disulfide will enable new modes of charge transport and therefore new device functionality. Specifically, that interplay between these defects in the bulk material will imply that the current voltage curve is quite different than you would see in a normal transistor. In particular, as you increase the voltage across the device, initially you're in a low current or high resistance state, but at some critical voltage it switches into a high current or low resistance state, and it stays in that state until you apply the opposite voltage. So you have a bistable switching between a high and low resistance states. This type of device is called a memristor because it remembers the voltage that was applied to it, and that dictates the resistance of the device, and it's potentially useful for so-called non-volatile memory like flash or USB memory that we use nowadays in our computers. Again, this is not new. A memristor is a two-terminal device that's been around for at least a decade, but because the constituent material is atomically thin, we can now gate the device and convert the two-terminal device into a three-terminal device. In particular, what we see is that as we change the voltage on the gate, we can tune either the voltage at which we switch between the high and low resistance states or the overall magnitude of the current in the device. This gate tunability is very similar to a traditional transistor. So in the nanometer limit, we now have the ability to combine two different devices into one, a memristor, which is good for memory, and a transistor, which is good for logic. And as what we call this device a MEM transistor. One detail, though, that I should point out is that this device does depend sensitively on the grain boundaries and their orientation with respect to the electrodes in the device. And that means you have a lot of variability from device to device, which I would contend prevents this from being scaled up to the wafer scale. And as a result, in more recent work, what we've done is change the design. Instead of having one grain boundary per device, we now have many grain boundaries per device. This now implies that we average over those different orientations at the device level, which gives us a high degree of uniformity, where we now have high device yield over large areas. The resulting MEM transistor characteristics still have the same attributes we had before. In the two-terminal response, a large switching between high and low resistance states. That's the memristive or memory effect. But also a strong tunability as a function of the gate voltage, tuning the absolute current level by another factor of a million. This then suggests that we could pursue technologies that need to have information processing and memory concurrently. And there is one example of this in nature, and that is the neuron. The neuron in our brains does this. It does memory and information processing in the same fundamental device, and as a result, this MEM transistor is a close mimic to a neuron. The other thing that neurons have that normal electronic devices don't have is many contacts in the brain. Each neuron is connected to 100 to 1,000 other neurons, which means many contacts are required. These devices, since they're planar devices, are amenable to additional contacts, and as a result, we can achieve a device structure which is increasingly mimicking a neuron and therefore has potential implications for so-called neuromorphic or brain-like computing, which will enable things like artificial intelligence and very low power computation. The very last example I want to give, and then I'll conclude, is a final mixed-dimensional heterostructure. In this case, we're going to combine graphene, which is two-dimensional, with nanoparticles of a material called lithium manganese oxide, which is a famous material for battery cathodes. This material has the distinct advantage that there's no cobalt in it. If we were to open up any lithium-ion battery in the room here today, we find that there's a lot of cobalt in the cathode. And cobalt is a problem because cobalt is mined out of the Congo in Africa, where there's some serious mining labor disputes occurring, and therefore supply chain problems for cobalt. So all the companies that are working in batteries want cobalt out. Lithium manganese oxide is an opportunity to do that, but the problem is that lithium manganese oxide in a battery has very poor stability because the manganese dissolves into the electrolyte, and that will compromise how many times you can cycle it. So our idea to overcome that issue was to combine lithium manganese oxide with graphene. Specifically, using our graphene ethylcellulose inks that I showed you before, we now add nanoparticles of lithium manganese oxide. When we evaporate away the solvent, we get a dense network, and we can see that the graphene ends up encapsulating each and every particle in the battery electrode. This few-layer graphene coating, since it's inert chemically, will suppress manganese dissolution and should, in principle, give us longer lifetimes for the batteries. So we can test that. We can go into the lab and build batteries. We can cycle them, charge and discharge them many times, and then look at the resulting capacity retention. And you can see in the green curves here that for a traditional lithium manganese oxide based battery that the capacity fades. This is something that we all encounter in everyday life. If you have an iPhone, you've used it for a year or two, you know that you have to charge it seemingly a lot more frequently than you used to, because it doesn't hold as much charge as it used to due to this fading phenomenon. That's a problem. The good news is that when you encapsulate it with graphene, since you've suppressed the manganese dissolution, that prolongs the cycle life and therefore gives you a longer lasting battery. There's another advantage, and that is in traditional batteries, you tend to have the constituent particles in the electrode relatively large because you want to minimize the contact area with the electrolyte. And when you have large particles, that means you have to diffuse lithium a long distance to fully charge and discharge. And therefore, the rate tends to be low for charge and discharge. I think we encounter that as well in everyday life. We have to charge our iPhones for hours, if not longer, to get a full charge. This is particularly problematic for electric vehicles, in that for electric vehicles, you've got to sit and charge for several hours before you can continue on your way. Whereas for a normal vehicle, we just go to the gas pump 5 minutes later, we're on our way with a fully recharged engine. What's my point? My point is that because we've controlled the surface chemistry of the lithium manganese oxide, we can now go to nanoparticles. Nanoparticles mean less distance for lithium diffusion and therefore faster charging and discharging. And we can see that very clearly. Here, what I'm showing you is a charging versus a charge capacity versus cycling curve, like I showed you before. But now we're going to change the rate at which we're charging. 1C means that we charge the battery in an hour. 20C means we charge it in 1/20th of an hour or 3 minutes. And you can see in the control, the normal battery, if I try to charge it in 3 minutes, I don't charge it very far. And that's, of course, what we experience in everyday life. Whereas with a nanoparticle-based electrodes, due to this very fast kinetics, we now get 75% of the charge in 3 minutes. This is completely game-changing, specifically for electric vehicles. We're working with Tesla as we speak. I'm trying to implement this for fast-charge electric vehicles to enable you to spend the same amount of time charging your electric vehicle as you do filling up your internal combustion engine at the gas pump. The other advantage of faster kinetics, faster speed, is that you can do things that would normally slow things down and still be okay. One thing that slows things down is cooling it down. For example, if you have a Tesla and you were trying to drive it today in Minneapolis, you would have less range than you would have in the summer because your battery does not work as well at low temperature. It's also true if you have an iPhone and you're on the ski lift, oftentimes your iPhone will stop working. It's not because the electronics have gone bad, it's because the battery has stopped working. Because we've improved the lithiation kinetics, we can now cool down our batteries and still maintain their performance. This is now at 0 degrees C, which is probably about the temperature outside right now. I think it's a little bit colder here in Minneapolis. And you can see that in the control, the battery performance is precipitously falling off even at 0 degrees. Whereas with the graphene coating, we now have very stable performance, high capacities at low temperatures, thereby enabling performance in normal operating conditions. Okay, with that, let me conclude. Try to make a few points today. The first is that centrifugal solution processing allows scalable production of highly monodisperse nanomaterials. This is technology that's been commercialized. We can also use tunable solution rheology to make printable inks compatible with additive manufacturing, including inkjet printing, gravure printing, screen printing, and 3D printing. And finally, we can utilize these atomically thin materials not only to make old technologies better, but to enable completely new types of devices. This includes the anti-antipolar diodes that I mentioned, the gate-tunable photovoltaics, the neuromorphic MEM transistors, and also the very high rate, wide operating temperature range lithium-ion battery technology. With that, I'll put up my final slide. I'd like to acknowledge my research group. This is a highly interdisciplinary team of undergraduate students, graduate students, and postdocs. Also like to acknowledge the funding agencies that support the work in my lab. And finally, thank all of you for your kind attention. Thank you.